Okay, so you just did an activity on pendulums. So we want to recap what you should have seen in that activity. So you have a pendulum that swings back and forth, and they swing back and forth very regularly and have been used to tell time for many long time. So in real pendulums, there's a string. I guess the string is white, which is why you can't see it. That must be it. Actually, I couldn't attach a string and make it do this in PowerPoint, so that's why there's no string. But anyway, so the time it takes to start from one end, go all the way to the other end, and then back is known as the period for a pendulum, which is the symbol is T. So it's the time for one complete cycle. So what will happen to the period if the mass is doubled? Okay, so here we've got a pendulum period mass m. Here we've got a period pendulum mass 2m. What did your experiments tell you? Let's see what this shows. It shows that it does not depend on the mass. So the period does not depend on the mass. So that will not show up in our pendulum equation. The mass will not. So you can think of basically as objects fall at the same rate. So this is a gravity factor. So it's not going to fall any faster because it's heavier. So that's why. What will happen to the period if the length of the string is increased? Okay. Well, that does have an effect on it, and as a matter of fact, increasing the length of the string has a pronounced effect on the period. Increasing the string length increases the period. So you can think of it as having more rotational inertia, mr squared, where the radius is the length of the string more or less. So that increased rotational inertia means it takes longer to get back and forth. What would happen if gravity increased? Okay, now this is a gravity affected phenomena. Okay, so if we had the Earth's gravity here, and then we had a stronger planet's gravity down here, the period is going to decrease. The frequency will increase, but the period is going to decrease. So again, this is relate this to falling objects. So how did the period was it affected by having small angles, increasing the amplitude of the swing? Well, at small angles, you probably didn't notice a difference. Like 5 degrees, 10 degrees, 15 degrees, maybe even 20 degrees. There probably really wasn't much of a difference noticeable. So increasing the amplitude at smaller angles, doesn't affect the period. So it behaves like simple harmonic motion at small angles. But at larger angles, it does have an effect. Okay. And at larger angles, it does take longer. So it's not true simple harmonic motion. It just approximates it at small angles. So we'll see why. So why is it similar to true simple harmonic motion, but not exactly? Well, if we look at the forces acting on the pendulum bob, we've got the force of tension in the direction of the rope, and we've got the force of gravity directly down. It does not undergo uniform circular motion because the velocity of it changes as it's swinging. This is tangential acceleration. So we're going to look at this as force of gravity. We're going to break the gravity in the component that's in the direction of going back to the equilibrium position. So the centripetal force. What is the centripetal force? It's the force of tension. That's our centripetal force. And what's acting as the restoring force? It's going to be this force of gravity in the x direction. So we're going to look at the gravity in the x direction. And that force of gravity in the x direction is going to depend on the angle. So it's going to be affected. As a matter of fact, it's going to be equal to mg times the sine of theta. So if we look at it at the bottom, this is the equilibrium position because there's no net force. and the restoring force is always going to drive it to the equilibrium position. So as we swing it up, this force of gravity in the x direction, that is the restoring force, gets more and more in the direction. The gravity gets more and more in the direction of that. So gravity gets more and more prone to drive it to the equilibrium position. So as it gets further away from the equilibrium position, the restoring force is increases, that's driving it back to that equilibrium position. And the restoring force always drives it towards the equilibrium position. If it swings on the right side, the restoring force drives it to the left, and so on and so forth. Similar to our mass on a spring, where is the pendulum's velocity the greatest? Okay, it's going to be the greatest at the equilibrium position, where the acceleration is the least, is 0. Okay. Where is the least acceleration? It's going to be at the ends, where the force is the acceleration is going to be the least. I'm sorry, the acceleration is going to be the least at the bottom, and the acceleration is going to be the greatest at the end, where the force is the greatest. Woo! I'm not sure what I said there, but if I can go back and wipe that. So the velocity is the greatest at the bottom, the acceleration is the greatest at the ends, just like on the mass on a spring. Sorry about that. So it's got the least acceleration at the bottom. So in true simple harmonic motion, the period doesn't depend on the amplitude, which we saw that that the pendulum's approximated. It's close. That's because the net force increases linearly with the distance from the equilibrium position. As we looked at before, the restoring force doesn't increase linearly with the distance from the equilibrium position. It increases with mg times the sine of theta. So it's a sine function. Now, while the angles are small, this sine function is pretty linear. Okay, it doesn't break from linear significantly until we get into the looks like the 30-degree range, and then it starts to break away from that linearity pretty significantly. But up until probably 20 degrees, it's pretty linear. So at small angles, it is amplitude independent pretty much. Okay, yeah. So the equation for our pendulum is t equals 2 pi times the root of L over G. Okay, just like we saw in our activity, the length of the period, or the length of the pendulum, as that increases, that's going to increase the period. Okay, gravity, if we were to increase gravity, that's going to decrease the period. And there is that square root function that we would have seen on those as well. So what we're missing is mass. We do not have mass in here. We also do not have theta. But again, this equation really only holds for quote-unquote small angles of theta, so probably to 15 to 20 degrees is when it holds pretty well. Okay. So how long of a pendulum would you need for a period of 10 seconds? Well, the equation is t equals 2 pi root of L over G. So plugging in 10 for the period, and then 9.8 for gravity, because we're assuming that we're on Earth. Okay, we're going to need a pendulum that's almost 25 meters long, so about 75 feet. So we would need a very, very long pendulum for a period of that time frame. Let's say we use that to measure time, and then we brought it from the Earth to the Moon. Okay, what's going to happen to that clock? Is it going to run fast or slow, or not change? Well, decrease in gravity is going to increase the period, meaning it's going to increase the time in between ticks. So it's going to run slower than if it were on the Earth. So don't take your pendulum clocks to the Moon. They'll run slow. Okay, so what I want you to do, or you can do, is numbers 1 through 11.5 in the worksheet packet. And if you have any questions, see me on the on office hours or virtual time. Okay? Bye.